Okay, continuing chapter 10, we want to actually now discuss more in depth something called the regression equation, or for us, the linear regression equation. And this is the default form of the regression equation that you'll see in the homework if you do help me solve this or whatnot. They always have this like number first, and then you have plus or minus whatever, and then another number times x. That's basically your equation. It's a linear equation that relates x and y, how they are related to each other. Now, when you do Lin-Reg t-test, okay, on your calculator, you actually get the equation in this form right here, a plus bx. And this actually is very similar to the old style you might have seen in algebra, where it was, y equals mx plus b, okay? The only thing is they swapped the b and the mx part in the order that they have them in is the only big difference right there, okay? So if you remember from algebra class, the m, when you look at that kind of equation, represents the slope of your line. So basically, how you rise and how you run, how your line basically changes over time, or changes for one variable of x, and then y. And then the b is your y-intercept, basically where your line strikes the y-axis. So whenever you have your equation, let's say, this is your line right here, right? Like y equals mx plus b right there. Well, the b is where your line would hit if it went back to the y-axis. It's a point 0 b. So that's your y-intercept for your linear equation if you were to graph something like that, okay, right there. Well, that's basically what we're looking at right here, okay? You're looking at the exact same idea that you had in algebra. It just is in a different form, okay? But no matter what representation you see, the important thing to remember here is this: the number that doesn't have the variable x beside it, that's always going to be your y-intercept. And then the number that is beside the x, that's always going to represent your slope. Okay, so regardless of what order you see it in, whether it's the one that's in the calculator or the mx plus b form that you're used to, it's all going to boil down to the exact same thing. So to do an example here, we want to take these right arm pressures and these left arm pressures and actually just find the regression equation that would be a linear model for this paired data. So I'm going to go ahead and enter in my list 1 as my right arm data, my list 2 as my left arm data. You may want to pause the video while you do that, but I'm going to go ahead and enter that now. Okay, once you get your list 1 and your list 2 populated with the data that you're given, we want to generate the equation of this line that would model your data. Well, you can actually do that with Lin-Reg t-test just like we used in the previous problems to find the p-value. Go over to test menu and then go up to Lin-Reg t-test right there, and we have all our data in where we want it right here. You don't have to have this REGEQ thing, so you can delete that if you don't need it. It's optional. And then calculate right there, okay? And you can see at the very top of the calculator screen, the form of the equation is a plus bx right there, okay? Where the variable x is a letter. Like you let it stay x. It's not a number that you know. So what you're going to have here is for your a, and if you look on your calculator screen, you see a is 43.56. If you scroll down, you can see b is 1.31. Maybe you want to do 3 decimal places. 2 or 3 is generally the rule. So we're going to say our prediction variable y is going to be 43.56. 4 will go up to 5 plus 1.315. 1.315. And then you're just going to put a variable x. You have to have that variable x. A lot of people leave that off. That variable x represents, the relationship between x and y. You have to have the x in your linear equation. And that will be your line of best fit that will model your data right there. And if you actually drew a scatter plot of your data and the line, you would actually see that line kind of going through the middle of the data of your data points right there. Okay. Now, the next part is making a prediction for some given X value. Now, some problems, they're going to say, okay, let's say that you had 100, right arm pressure. What is the Y value going to be for that? And you could probably look at the data and kind of make an estimate of what you think is going to be close to. But when you're doing the homework, you have to figure out, is there a linear regression for this problem or not? Okay. So what you're going to do is break it down into two scenarios. Okay. You're going to have option 1. I'm just going to call these option 1 and option 2. Option 1 says if you don't have linear correlation, so in the case that the p-value is larger than 0.05, you're actually going to say the best predicted value for the Y is going to be the average of the Y with the bar over it. So you take your Y's and average them up. Okay. Now, if there is linear correlation, if the p-value is less than 0.05, basically, your best predicted Y value is going to be found by substituting the X value into the regression equation, the equation you just found, actually. Now, on that previous problem, okay, you can see we still have it up on LinReg t-test right here, over on the side. But we saw that the p-value is 0.05699. So the p-value for those 100 arm pressures was 0.05699 right there. Okay. Well, that is larger than 0.05. So there is no linear correlation between the right arm and left arm blood pressures. Okay. Because you can say this if you want to, because the p-value is larger than 0.05. Now, they say in this problem, okay, if you're given a right arm blood pressure that's 100, so you're given an X that's 100, what will the predicted Y be for the systolic blood pressure, the Y value? What is your prediction going to be? Well, which option do we pick of the ones above? Since we have no linear correlation, we're going to pick option 1. So use option 1. We're basically going to average our Y values. Okay. Average Y values. And you can easily do that. Since you have all your Y values in list 2 already, you could actually go to stat, go to one var stats, and just do one var stats on list 2 alone, right there. And you'll get an average of 163.2. And that'll be your predicted, your Y hat is your prediction Y. 163.2 will be your predicted value for the left arm pressure given the right arm of 100. Okay, so basically if you had another point right here, this value right here, whenever X is 100, Y is going to be 163.2 prediction. Basically is what you just found. So you're making predictions for a given X right there. These problems get a little tricky because they don't ask you a lot of times about linear correlation or not. You have to kind of do that in the background. So you have to figure out if it's option 1 or option 2 before you try to go at an answer for the problem. Okay, look at this next example and I'll show you what I mean by this a little bit more. Okay. This is a problem very, very similar to a homework problem, and the only reason I put it in the notes is because it often just, confuses students. But this one says 50 randomly selected speed dates. They have attractiveness by males of their female partners, X. So basically, the men rated the women like 1 out of 10 is basically what happened here. And then the females got to rate the males of their speed date partner, which will be our Y values. So the females' ratings were the Y. And you can see here the 50 pair data, which we don't even have the data. They don't give it to us in the problem. But we actually do have enough information to figure this problem out. Okay, but the 50 pair data had averages of, and it says X, the average of the men's ratings, it was 6.5. So the average of women that they rated or whatever they say is 6.5. And the average of all the women's ratings ended up being 6.0. So you see the men were already on average more generous than the women were with their ratings right there, right off the bat. But anyway, and then it says, we want to use Lindbergh t-test, or it said they did use Lindbergh t-test to get a p-value of 0.203 for the paired data. And then they got the equation, the regression equation, to be that 7.36 minus 0.210 times x. It says use the significance of 0.05 and complete the parts below. Okay, now this is classical prediction problem, or it will be in a second. You'll see how it unfolds on the second part below. But it says using the information, would there be a linear correlation between the x and the y values? Why or why not? Well, you have to figure out like what piece of information in that whole paragraph do we need. There's a lot of numbers going on, and we have to figure out like what exactly do we care about, or do we need to pull out to figure out if there is a linear correlation or not. And it's the p-value right there. So since the p-value was 0.203, that right there is greater than the 0.05. So we're going to have no linear correlation. Okay, since we don't have any linear correlation now, though, what are we going to do for this next part? It says, using your answer above, make a prediction for the attractiveness the female would give the male if you know the man gave her a 6. Okay, so he said she was a 6. What is she going to return saying he is? Right there. Okay, so we got to figure out which option we're going to use to make this prediction. Well, since we had no linear correlation, we're going to have to say option 1 will be what we go with here. We're going to have to say use the average of the y values, so you don't have to substitute into the equation. Well, the average of the y values was also a 6. So y with the bar over it, which is the average of all your women's ratings, that will be 6.0. Okay, so use option 2. The average of the y values, which we don't have to calculate anything because it's actually in the problem itself. So y bar equals 6.0. Okay, or sorry, we're predicting, so we're going to say y hat equals 6.0, but y bar was the number we used for that prediction, that y hat. Okay, but there you go, option 2. Go down to the next problem right here, and let's do one right here where we have a large list of data here of old and new fuel economy ratings, and right here we're going to see if there's a linear correlation or not. I'm going to give you some chance to enter this data right here into list 1 and list 2. Okay, right there. And you can pause the video and enter this data on your own. Okay, once you get your data entered into list 1 and list 2, now you're ready to go ahead and go into Lindbergh t-test to see if there's going to be linear correlation or not. Right there. And I'm going to go ahead and go to calculate here, figure out what the p-value is. On this one, I get a p-value that's really small. So I'm seeing on my screen 4.0 104, basically, e negative 12. So I'm going to have like 12 zeros right here. And then 104. And then a decimal between my first two zeros. That is definitely smaller than 0.05. So we're going to say yes, there's linear correlation. Okay, now on this problem it says, based on your answer above, find the best predicted new rating given the old rating is 19. So they say, okay, the old rating is 19. What would be your new rating? And you can kind of, look at your data and tell, but we want to use the prediction options from above right here. So if you look here, if there's not linear correlation, we use option 1. But since we did have linear correlation, we're going to pick option 2 and substitute our x value into the regression equation. So we're using option 2. Use option 2. The regression equation. So our regression equation, we can see it on the calculator screen. It's the y equals a plus b x right there. So our regression equation is going to be 0.808 plus, and then 0.863 times x. And now the only thing left to do is just say, okay, well, 19 when it's x, since we're using the regression equation, we're going to sub in 19 for that x spot and figure out what is this going to simplify down to right here. So you're basically plugging in the 19 where the x is. And you can use your calculator to do this. If you just hit clear, you can do 0.808 plus 0.863 times 19, all in one fell swoop, and then we'll get y with the bar over it, 17.205 right there miles per gallon. Or you can just do 17.2 if you want to, which is probably good enough, honestly. So 17.2 miles per gallon, and that's how you use your regression equation, okay, when you want to make a prediction. If you have linear correlation, you can use the equation. If you don't have linear correlation, you'll have to average all your new mileage ratings to see what the average is of them, which you can do with one of our stats on list 2. Now, the only other thing I want to talk about is just interpreting the slope for your regression equation. And if you remember, and sometimes they'll call this marginal change in the homework, but if you remember, the slope is always going to be the number, or the rate of change of your line is the number beside x right there. So in this problem right here, it says, there's a regression line where x was consumer price index and y was the cost of pizza. Well, one thing you can do to interpret your slope is just take it as a number and write it over 1. And if you remember, rise over run is your slope. So the top number describes the rise, and the bottom number describes the run. Rise is a y value, so this would be cost of pizza. Then the bottom number would be your CPI, your x variable. Okay, rise is y, run, left and right run on the bottom, is your x, so that would be CPI. So here's what you basically have. For each 95 or 945 based on 95-cent rise in pizza, your consumer price index will go up by 1 as well. So as the cost of pizza increases by 95 cents, the CPI, you can say, increases by 1. You can also turn it around and say it the other way around, like CPI, use it first. As it increases by 1, the cost of pizza also increases by 1. or sorry, increases by 95 cents. And then more colloquially, probably the easiest way to say it, like as far as a phrase, is for each unit of CPI, the cost of pizza increases by 95 cents right there. That'd be probably the easiest way to say it, just like, how you describe it if you're talking about economics or something. Now, that's a positive slope right there. That ended up being a positive slope. What if you have a negative slope? What if you ended up having a negative 0.945 as your slope? Well, you can actually write this one of two ways. You could actually write it as negative 0.945 over positive 1, or you could actually write it as positive 945 over negative 1. You can actually pick whichever way you want to as far as like that representation right there. So if you're using that first way, you would say, okay, since it's negative 0.945 on top, you'd say as the cost of pizza decreases by 95 cents, the CPI increases. So negative slope has, they're going different ways. And then if you were doing it the second way, or what's that other option? You could say as the cost of pizza increases by 95 cents, the CPI will decrease by 1. Okay. You could also say for each unit CPI, the cost of pizza decreases by 1. Right there. Might be an easy way to verbally explain it. Now, when you're doing a negative slope, you cannot make both the top and the bottom negative. You can't do both because that'll end up being a positive slope. So that'd be just like we kind of did that first problem right there, where they're going the same direction right there. But when you have negative slope, you just assign either numerator or denominator the negative, and then go from there with your interpretation. Look at that last problem where we have the 0.808 and the 863x. So we had this regression equation here. Okay. We want to interpret the slope of this. So let me rewrite this equation right quick. Okay, so for our slope, our marginal change right there, how do we write a sentence interpreting that? Well, the slope, just pick it out. Which number is it? It's the number in front of x, so the 863. 0.863 over 1. And remember, this is rise over run. So remember, rise is y value over run is x value. Right there. Well, y values from that last problem, the y values were the new ratings, and the x values were the old ratings. So new is on top, and this is the old on bottom, right there. Okay. So here's how we're going to interpret this. You could say as the new ratings increase by 0.863, the old ratings increase by 1, or maybe just an easy way to say it, for each 1 mile per gallon old rating, the new rating increases by 0.863 miles per gallon. Something like that would be an easy way to talk about your new mileage rating and old mileage rating relationship right there. And you can see like the new mileage ratings are not as increasing as much as the old. Like each one of the old basically is a portion of that, like 0.863 of the new. And you can even see that with the problem, like the data itself. If you look at the old rating, it's slightly higher than the new rating right there. So it kind of makes sense just by us looking at the data too, so we should see like that makes sense. Now, one other thing I want to talk about is just a bonus thing here, but something that's in your homework a little bit too is this 808 number right there. Okay. Let's talk about it just a little bit. So that number is what we call the y-intercept of your line. And it's always a point, 0, comma, And for this case, it'll be 0.808 right there. Okay. Sometimes they want you to interpret what the y-intercept represents. And I will say, for some data sets, or for some regression equations, it won't make a lot of sense. And I think this one is a really good one to highlight that. But if you remember the x value, remember that's your old ratings. So that's your old ratings, and this is your new ratings. When you talk about, x and y, right? Like that's what an ordered pair is. It's an x, which for the y-intercept it's always 0, and then a y, which for us it's that 0.808 number right there. Okay. Well, what's the interpretation of this exact point? When the old mileage rating is 0 miles per gallon, what will the new rating be? The new rating will be 808 miles per gallon. And, a lot of times I think you can think about why in the world is this kind of nonsensical? Because, if you have a car going 0 miles per gallon, which that probably does not exist, but theoretically, if you had that, the new one should also be 0 miles per gallon as well. So it should be 0. But the reason it's off a lot of times is you don't have data that goes back that far, like that close to 0, to test. Because there's no car that exists that goes that low of miles per gallon. So, you're not going to have data that far back. So sometimes your regression equations will be off just a little bit. And that's like we talk about error with our equations. You do have some slight errors that can occur with your equations if you get really far away from your data. Like the lowest value we had for the old mileage rating, the lowest value we had was 16, it looks like right here. So yeah, if you go really far away from that, like 0, you're definitely going to have some distorted value, some error with your line as you go away from your data set. So just something to remember with regressions. They can only kind of predict up to certain points, like within the range of your data, the scope of your data. But they are useful. It is useful to learn about and know about how to interpret regression equations, and of course the slope and the y-intercept as well.